so let's give you a quick review for previous class. We talked about when you deal with a non-steady state diffusion process in solid materials, the material system is quite important. And actually, there are three different typical examples. And we already introduced you how to get the solutions for diffusion couple, which means you can get the concentration of diffusing atoms as a function of location and time, right? And do remember the solutions for that? Okay, so after serious deviations by solving the differentiation equation, in the beginning, it was a partial differentiation equation with two variables, shown like this. And when you inserted when you introduce a dimensional variable eta, then we converted this partial differentiation equation to ordinary differentiation with just one variable. So that will help you to easy to get the solutions for this kind of diffusion couples. So the results demonstrate that the concentration of diffusing atoms equals to what? The average of sum of Cr and Cl plus the average of the difference between Cr and Cl error function eta. And we also mentioned if we want to directly use these solutions, there are three concentrations at different locations does not change with time. The first one will be at the center or interface of this diffusion couple, the concentration should maintain at the average of Cr plus Cl. And also to end of this diffusion couples, the concentration should remain constant at Cr at the x approach infinity, which means the right end of the samples, and the left end of the samples, the concentration should maintain at Cl. So now you have, and this solutions can solve this kind of step function, right? Okay, so let's move to the second case. People call it is limited diffusion source. So you can consider that the example will be like you deposit a very thin layer of diffusing atoms on the top of your substrate, and you heat samples up and allow diffusion happens. So because the diffusion source, you only have limited diffusing atoms. So under these situations, the surface concentration of these diffusing atoms will decrease over time. So the characteristic for this type of material systems, we can see that the concentration of diffusing atoms on the surface will decrease over time. And then we give you examples here. If you have a copper nickel alloy in between pure nickels, and we are interested in on the concentration of copper as a function of time during diffusion. So we try to plot the concentration profile of copper, and here is C0. So you can get the concentration of copper can be drawn like a square function. Some people call it as a one-dimensional square function, right? And the thickness of this diffusion source or this copper nickel alloy, we call it as the thickness is delta x. Okay, so in order to solve or get the concentration profile of this copper, so we can use the technique we call the superposition. Superposition means we can stake two functions together and to assemble this kind of square function. So based on what we learned in previous case, we know we know the solutions for step function, right? So how about if we can stake two step function together to get this square function? Then that's what we call that we can easily get the solutions for this square function, right? So we are going to use this superposition technique or methods to separate this square function to become two step functions. The first one shown in blue and the second one shown in green line. So that allow us check first, okay? So from the negative infinity to 0, if you sum the blue line and green line together, then the value, the concentrations will remain 0. So it's 0 here, right? And if we focus on between the 0 to delta x, then if you sum these two lines together, then the concentration you have is C0. So we check doing the 0 to delta x, the concentrations, yes, is C0, right? And if the x is larger than delta x, then we try to sum the C0 and minus C0 together, so the concentration was 0, right? So if x is larger than delta x, and the concentration remains 0. So yes, we can use these two step functions to get this square function. So based on this idea, so let's try to get the solutions for this square function. So we got the two curves, right, for step functions S1. So we got the boundary as we mentioned before, and don't forget do you remember the solutions for this step function is surely here, right? The average of sum of C0 plus 0 and plus the average of difference between C0 and 0. So it's C0 minus 0 and error function eta. It's a solution for S1. And how about the solutions for S2? The boundary actually listed here, so you can check that. But you can directly write down the solutions, right? It's the average of minus 0 and 0. So it's a average of minus 0 plus 0. And also plus the average of difference between negative or minus C0 and 0 means a minus C0 minus 0 and error function eta, right? But however, error function eta, you need to modify that because the 0 point was at here for this square step function, right? But for S2, actually the 0 point is shift to delta x, so we need to minus delta x. So take a look here. We highlight, so the upper limit should be changed to eta minus delta eta, because this curve was shifted from x equals to 0 to x equals to delta x. So now we get to solutions for S1 and S2, right? So we just sum these solutions together. So we just list here. So we delete these two terms and combine these terms and these terms together. So you delete the 2. So what you left is a C0 divided by square root of pi. And the list integral term actually we just list here, but if you take a look here, we can combine these two integral terms, right? The first one actually is you integral from 0 to eta, this term, and the second term, so the second term is minus, right? Minus the second term actually is minus the integral from 0 to eta minus delta eta. So be like this. So you use this term integral to minus this term. So what you left actually, use the other color, is this region, right? Is from integral from eta minus delta eta to eta. So from eta minus eta to eta. So this is a solution for this one-dimensional square function. Okay, so this is once this is you can use this two curves to get the solutions, but we also provided the other method we call a solution tool. Some people probably will question why can we in superposition these two step functions. The first one is we show here in the blue curve, and we use this one to minus this step function. And if you use this one to minus this one, and only you get is the square function, right? So then because this one, so you also need to list the solutions for S1 is the same with previous method, but only different I believe is the solutions for S2. S2 actually you can easily write down the solution, also the average of sum C0 plus 0, and also plus the average of difference between C0 and 0, so it's C0 minus 0, but the error function iota. But here you also modify the upper portion, right? Because the curve actually shift from x equals to 0 to x equals to delta x. So here you need to modify as iota minus delta iota, and you sum this together and also get the same results shown here. Okay, so next I'm going to focus on these solutions. So I just copy the solutions to next slide, and we are going to explain more about the solutions. Okay, so these solutions actually what you have here is you have a C0, actually is a concentration of these diffusing atoms, right? And you got the integral distribution from iota minus delta iota to iota. Actually, it will be the thickness of these diffusing atoms is quite important to affect the concentration distribution of the diffusing atoms, right? So that's allow, and we assume the delta iota is smaller than iota. What this means? This means that the thickness delta iota of this diffusing atoms is much smaller than the size of sample or the thickness of the sample, diameter of the sample. Compared to the diameter of the sample, this diffusion source is quite small. Under these conditions, and we also assume the concentration inside this thin diffusing atoms remain constant. This constant means the concentration of the diffusing atoms inside this layer is remain constant. So under this situation, we can take this integral turns out we can use the delta iota to substitute this integral term. So that will become like this, right? Because we use the delta iota to substitute this integral term. Okay, and next, what's the delta iota? Actually, is the delta x divided by square root of 4dt. So we just converted iota and express that in x and dt as a function of x and dt, right? And next, what's the C0 times the delta x? Delta x is the thickness of diffusing atoms, so it times the concentration of the diffusing atoms. So you will get the ND will be the source. We call it the source strength. So if the unit for concentration part will be the numbers per univalent, per valent, so you times the distance, that you will get the area density, right? So ND also can express like this. If you integral the whole space from negative infinity to infinity and integral concentration along whole space, then you will get the total source strength in this case. Okay? And we want to talk more. For this case, some people call it as a one-dimensional diffusion case because the concentration profile majorly change along this dimension, this one dimension along x, right? So for this case, some people also call this kind of diffusion case belongs to one-dimensional diffusion case. So are there any other diffusion case also belongs to one-dimensional case? Yes, you can check your textbook page 103, and there's a table 5.1 list different dimensional diffusion. For the one-dimensional diffusion, we just talked about that. Is there are also two examples also belongs to one-dimensional diffusion case. Okay, so what are they? So I actually instead of just use some description here, I draw some pictures. I grab some pictures to demonstrate. This also belongs to one-dimensional diffusion case. For this one is the one we just introduced to you, right? You got the planar diffusion source in your matrix, and a lot of diffusion happens. Then the diffusion source is diffused toward the left-handed side or right-handed side. So the distribution will majorly along one-dimensional. So we call this a one-dimensional diffusion case. But we still have two cases can consider also as a one-dimensional diffusion case. The first one is the point source deposit on a narrow wire. So we got the point source diffuse along narrow wire. So this point source can either move to the left-handed side or right-handed side. So it also belongs to one-dimensional case. Or you got the light source. For example, you have a narrow wire deposit on your substrate. Secant substrate. Secant substrate maybe is not really correct. You deposit on a planar source. A planar source. So in that case, this is a plane, right? So the diffusing atom can either move to left-handed side or right-handed side. So it also belongs to one-dimensional case. So because of just the diffusion atoms can move just along one directions. So this three case belongs to one-dimensional diffusion case. Okay, so let's move back here. So based on this, we know the concentration profile of diffusing atoms in a one-dimensional diffusion case can express like this, right? And the ND actually is related to the source strength of diffusing atoms, right? And some people probably were wonder, Professor, in most of case, we know the ND, right? Because we deposit or we create or insert a diffusing layer inside this three-dimensional matrix. So in most of cases, we know before diffusion, we know the ND, right? What's the area density of our diffusing atom, right? So we can we know the value for ND before diffusion. If we created these materials, then for sure we know the area density for these diffusing atoms. Why we still need to use these equations to get the ND is quite weird. The only reason to tell you this relationship to get the ND is only happen in one kind of conditions, when you are not the people who created these materials. So when you have these materials, diffusion already happened. So under this situation, you don't know the exactly ND, right? Exactly value of ND. So under that situations, after diffusion, and we already we have that samples, right? Then you can section that samples by EPMA to plot the concentration profile of diffusing atoms to get a C of X. Then integral all spacemen or integral from integral all samples, then you can get the ND. So this this is the other approach to get the ND. If you are not the one who created these samples, so you don't know the ND, right? So here we also provided you the other method to get the ND by just section your samples and analyze by EPMA or SIMS and integral whole samples, then you can get the ND. Okay. And also, we also highlight that the unit of ND varied with different kinds of source. What this means, different kinds of source. Let's move to these examples. We have different kind of source, right? This is point source, line source, and also planar source. So the ND, the unit for ND will be different, right? For point source will be the number of atoms, diffusing atoms. For the line source, the unit will be the numbers of diffusing atoms per distance or per length. For planar source will be the area density, right? The numbers of diffusing atoms per unit area. If you input this ND here and to calculate the concentration of diffusing atoms, different source, you will get a different unit for concentration. You are going to describe these materials. As we mentioned, the ND is here, right? And what's the unit for the explanation? We don't have any unit for explanation term, right? So the bottom part actually is the unit for diffusivity is expressed like here, right? It's a meter square or area per second. So you times the time second. So what you got is you got the area, or you got a meter square. You take the root on meter square, so you got the distance on the bottom. So you use the ND to divide the distance, you will get the concentration, right? So for the point source, the concentration after calculation, you got the numbers of diffusing atoms per length. This is per area, and this is per volume. Okay, so this is what this means. The unit of ND will vary with different kinds of source. And this is one-dimensional diffusion case, right? But sometimes the diffusion not only limited to one-dimensional. Sometimes we talk about will be two-dimensional and three-dimensional. So how to modify the solution we get? For three-dimensional case, actually, the concentration part we just this is just for one dimension we got x, right? So three-dimensional you got x, y times y, and z. Okay, so this is the solutions for three-dimensional diffusion case. And the only difference actually it will be focused on here. This is 3/2. This is 1/2. And the exponential term here, this is only along x, and this will be r squared. It's related to x squared plus y squared plus z squared. And also, if you are not the people who fabricate these samples, so you don't know the ND, then this also provided you the other approach to get the ND. As long as you know the concentration profile along x, y, and z, then you integral the negative infinity to infinity along x, and also integral from the negative infinity to infinity along y, and also integral the negative infinity to infinity along z. Okay, so this is how we deal with if you have three-dimensional diffusion case. So now, next I'm going to ask you, we have one-dimensional, three-dimensional, and how about two-dimensional? Can you try to formulate the solutions on the concentration of diffusing atoms? Probably you will say, oh yes, this times this, right? Yes, you are right. So the concentration profile here will be 2/2, and here r squared actually is x squared plus y squared. And this is two-dimensional diffusion case. So what are the examples would be belongs to two-dimensional diffusion case? I will say the point source in two-dimensional. So what this means? The point source, I draw a point source and two-dimensional. So you got a point source, you deposit a point source on a plane, on a film, very thin, one layer film with only one layer. So it's a thin layer, thin film. So this point source can diffuse either along X or along Y, so it's two-dimensional diffusion case. Or you fabricate a narrow wire into a three-dimensional matrix. So, right? So also diffuse either along this way or along this way. So also belongs to two-dimensional diffusion case. And how about three-dimensional? It's quite easy, right? You just deposit or insert, for some reason, a point source into a matrix, three-dimensional matrix. So this diffusion, atoms can either diffuse along X or Y or Z. So it belongs to three-dimensional diffusion case. Okay? Okay, so we finish this part. So I'm going to, before we ended this example, so we try to give you examples which we call is a nickel copper diffusion couple. And what we have here is, yes, we have a thin copper nickel alloy in between pure nickel. And this the thickness of this alloy is very thin, it's 0.5 micrometer. And based on this, you can determine, you know this is belongs to, because the copper can diffuse either to left-handed side or right-handed side, so it belongs to one-dimensional diffusion case. Under this situation, you can directly formulate these equations. And we try to know the D, right? So D, the question tell you D equals to D0 exponential term, and also provide the activation energy, D0, and also the temperature. So based on this, you can calculate the D of copper expressed like this. So D, you got the D, right? And NX actually, in most of case, will tell you, in this case, it's a 60%, right? Okay, so now, as long as you know the NX, D, then the only one you don't know, you can easily draw the concentration as a function of X and T, right? As long as here they plot the T equals to 30 minutes, 1 hour and 2 hours, so you got the concentration profile. You can see that the concentration decrease over time. So this is for sure belongs to limited source, right? Okay, so you can easily write down the solutions for this kind of diffusion case with limited diffusion source. But this is the limited source one for sure. So, and there's the other case also belongs to limited source one. It's not, you have the diffusing atoms in between two materials. How about if I deposit a very thin layer of diffusing atoms on our substrate? And under these situations, the diffusing atoms can only go into the substrate, not go two directions. In this case, the diffusing atom can either go left-handed side or right-handed side, right? But if I deposit a limited source on the top of our substrate, so the diffusing atom can only go one direction to right-handed side, right? So under this situation, the solutions for this one, we call a semi-infinite median. For this one, we directly times the 2. So times the 2, you can delete the, times the 2 means what? Square root, you get a square root of 4, delete this term out, so you got this one. Solutions for this case, also this limited case, we call a semi-infinite median. And for this one, some people call it the diffusing atoms belongs to infinite median. Okay, semi means the semi because you have only one half a matrix, and this you got the diffusing atom can either go to the left-handed side or right-handed side. So some people call it the infinite median. Okay, so we finish the second case is with a limited diffusion source, and the characteristic for this one is we can observe the concentration of diffusing atoms decrease with time.